telescope is the most important instrument in learning about space. Over time, telescopes have improved in technology as well as in size. Today's video, we'll talk about some of the huge telescopes under construction. These telescopes allow us to observe extremely faint light in different parts of the universe. With these telescopes, we can search for the first galaxies after the Big Bang and observe the evolution of galaxies, from the first formation of galaxies to the present state, and observe the formation and evolution of stars and the formation of stars and planets. The scientific community is very optimistic about these telescopes. The size of the mirror in the telescope is very important in any telescope. The larger the mirror size, the more light the telescope can capture. This will result in clearer images of more distant objects. In 1839, Irish astronomer William Parsons designed a huge telescope to uncover a mystery, and that mystery was some brighter than usual spot in the sky that we now know as the galaxy center. At the time of William Parsons, concave mirrors were made by hand, making large-scale concave mirrors very challenging. William Parsons came up with a solution and made a concave mirror 6 feet in diameter that weighed about 3 tons. This is the historical telescope of William Parsons, which started operation in 1845. The diameter of the mirror in the existing ground-based telescopes is roughly 3 to 10 meters. For example, the 2 mirrors in the large binocular telescope each have a diameter of 8.4 meters, which is larger than a 2-story building. Again, the very large telescope has 4 mirrors of 8.2 meters, and these 4 telescopes work like a single telescope. The resulting mirrors collectively act as a mirror of size 130 meters. The method by which these 4 mirrors are combined is called interferometry. And interestingly, this is how the black hole at the center of the Milky Way galaxy was photographed. Telescopes are currently being built with larger mirrors than ever before and advanced technology. First on our list is the Giant Magellan Telescope, abbreviated as GMT. The Giant Magellan Telescope is going to be the world's largest telescope in the search for Earth-like planets in other solar systems. It is being built in the Chilean desert to observe the skies of the southern hemisphere. The Giant Magellan Telescope will use a total of 7 mirrors with a diameter of 8.4 meters with a combined diameter of 25 meters. But a large mirror alone is not enough. The mirror has to be perfect to capture light from distant objects. Therefore, the mirrors of all telescopes today are made specially. In this case, first a huge rotating structure is made and then the glass is placed on it. After placing the glass, it is heated to temperature of 1200 degrees Celsius, so that the glass melts and turns into a liquid. The entire structure is then rotated to form a concave mirror in glass. If you notice, you will see that if the water container is rotated, the water in the container takes a parabolic shape. This happens mainly due to centrifugal force. However, the molten glass is slowly cooled as it rotates. 3 degrees Celsius per day is completely cooled in 3 months. Thus, a large-shaped parabolic glass is obtained. The glass is then polished very carefully. After this is done, a very thin coating of aluminum is applied so that the glass behaves like a mirror. The glass is first placed in a vacuum chamber to coat the aluminum. The aluminum is then heated and vaporized, and the vapor is sent to a vacuum chamber. As a result, a very thin layer of aluminum is formed on the glass, which is basically how mirrors for telescopes are made today. These mirrors will be so perfect that if we consider a mirror to be the size of a whole America, there will be only half an inch of imperfection between them. Each of GMT's mirrors takes about 4 years to make. Keeping the primary mirror cool is very important in any telescope. To keep the primary mirror of the ground-based telescope cool, holes are kept at some places behind the mirror. When the telescope is turned on, cold air is applied to the holes, which keeps the primary mirror cool. But in the case of any telescope, the primary mirror as well as secondary mirror are very important, especially for ground-based telescopes, because the atmosphere is a major obstacle for such telescopes. As a result, it is very important to consider where the ground-based telescopes is being placed. A ground-based telescope is placed as far away from sea level as possible. Also, there should be no light pollution in places far away from the city. Also, care is taken to ensure that the climate where the telescope is being installed is dry, because clear skies can be seen in dry weather. Even after maintaining all these things, the effect of the atmosphere does not end. And then comes the secondary mirror of the telescope. Parallel light waves from distant objects are no longer parallel due to the atmosphere, resulting in blurred images in ground-based telescopes. To solve this problem, a very sensitive motor piston is installed in the secondary mirror. This piston pushes the secondary mirror and bends it on the millimeter scale. As a result, parallel light waves coming from distant objects become unbalanced due to atmospheric effects. But after that light is reflected on the primary mirror and goes to secondary mirror, the motor piston rearranges the light waves by bending the secondary mirror as needed. This results in a final clear image. This technology is called adaptive optics. Currently, this technology is very advanced. Think of it as an infrared image taken with an ordinary telescope. In this case, the image looks very blurry, but this same image can only be obtained with Hubble 2.5 meter mirror because Hubble doesn't have an atmosphere problem. Images seen in the 6.5 meter mirror of the James Webb Telescope. But because of the adaptive optics in GMT, such an image will come. Then you can understand how advanced the current adaptive optics technology is. GMT will be a telescope so powerful that it can detect planets that are 20 million times fainter than their star. GMT will monitor the rotation, mass, and atmosphere of those planets. It will also observe how stars are formed, as well as working with a black hole and observing what happens when a black hole engulfs a star. GMT is expected to be operational by 2030. Second position in the list is Extremely Large Telescope, abbreviated as ELT. Just by hearing the name, you understand that this is going to be the biggest telescope. In 2000, ESO proposed a 100-meter telescope with a budget of 1.5 billion euros. However, the probability that such a large telescope would work properly was 75 to 92%. As a result, this project was not approved. Later in 2011, the size of the telescope was reduced 39.3 meters, resulting in a budget of 1.1 billion euros. Currently, the construction of these telescopes is going on in desert of Chile. The ELT's primary mirror consists of 798 hexagonal mirrors that together form a 129-foot mirror. The secondary mirror will be 4.2 meters and weight about 3.5 tons, making it the world's largest secondary mirror. It will also have an advanced adaptive optics system which will have 8,000 pistons. And with these 8,000 pistons, the secondary mirror can be readjusted 1,000 times a second. Also, these telescopes will have 8 powerful lasers, which will act as an artificial guide. The ELT is expected to capture images 16 times clearer than Hubble. Also, it is expected that these telescopes will be ready by 2027, which will observe the first galaxy, supernova, expansion of the universe, black hole, exoplanet, etc. Third on our list is the 30-meter telescope, abbreviated as TMT. After hearing the name 30-meter telescope, you understand that the diameter of the mirror in this telescope will be 30 meters. But in the case of the 30-meter telescope, the single mirror will not be used. The TMT will have 492 hexagonal mirrors joined together to act as a single mirror, much like the James Webb Telescope. TMT's mirror will be very thin, at just 45 millimeters or less than 2 inches. As a result, mirrors can be easily manufactured, transported, as well as easily replaced. Along with that, adaptive optics must be there. In the case of TMT, the light reflected from the secondary mirror can be taken in different directions as desired, so the light can be analyzed in any scientific machine as needed. Plans were made to view the northern hemisphere sky through the TMT, so the top of Mauna Kea was selected as the site. But things got complicated when some locals started agitating against the project. Mauna Kea was a sacred place for some of the local people. According to their belief, some of their god resides in that mountain. This incident happened in 2009, although the incident started much earlier. Some telescopes had already been installed on Mauna Kea. However, some environmental groups there claim that the telescope authority had not kept the promise it had made to protect the environment. Mauna Kea mountain is the most ideal place to see the northern hemisphere. It is expected that this TMT will provide 10 times clearer images than the Hubble telescope. The fourth and last telescope on our list is the large Synoptic Survey Telescope. It will not be as big as other telescopes. The mirror diameter of this telescope will be only 8.4 meters. However, the work of these telescopes will be different from other telescopes. These telescopes will survey the entire sky. On average, about 1 million supernovae are formed in our universe every day. Along with the expansion of the universe is constantly changing due to these reasons. This large Synoptic Survey Telescope will observe all these changes. The telescope houses the largest as well as the most powerful camera in the world, whose length will be 1.5 meters. As a result, it is going to be the world's most high-resolution camera. The single image resolution of this camera is 3.2 gigapixels. This telescope will take 800 images of the sky every night. Each image size will be 3.2 gigapixels. That is, this telescope will generate 15 terabytes of data every night. Thus, if these telescopes provide 10 years of service, it will generate a total of 15 petabytes of data, which is a very large amount of data. All the telescopes I have mentioned so far have complex engineering behind each telescope. For instance, there is another form of engineering for the movement of the entire structure. Another kind of engineering is to maintain airflow. In this way, all these modern telescopes have been developed by combining the talents of many people. Friends, how do telescopes work? What is the history of telescope invention? And what types of telescopes are there? Watch this video to learn more about how humans started to see space through telescopes. And if you like the video, you can subscribe to our channel.